All right, gang, Math 5130. Going to be a lot going on in this video. I'm going to use R first, and then I'll demonstrate how to make these calculations in StatCrunch. But the first thing, regardless which statistical software package that we use, we're going to see something new, and that component that's new is going to be the assumption test that we have to check before running, in this case, the independent samples t-test. Now, the assumptions are we have normality. And for normality in this class, we will run what's called a Shapiro-Wilks test. And I'll demonstrate the commands to you here in just a second. The null hypothesis for the Shapiro-Wilks is the population distribution is normally distributed. And the alternative hypothesis is the population distribution is not normally distributed. Now, the test statistic for the Shapiro-Wilks is a W statistic, so we'll report that. And then we'll report our p-value. Again, if it's less than 0.05, less than 0.01001, demonstrated that in a previous video. So you should know how to do that. If not, you should go back and rewatch that video. The other assumption that we have to check for the independent samples t-test is the equal variance assumption. Now, what this does, if you think back to the data set that we created in the previous video of close SP over false status, which you can see over there, over on the left side of the screen, we need equal variances. So the variances for close SP across patients who did not report a fall versus the variance of close SP across those who did report a fall need to be equal. And we will use, in this class, Levine's test. Now, there are different tests to check for normality other than Shapiro-Wilks. I use this one because it's just the most commonly reported. And the same thing with equal variances. There are other tests for equal variances, but Levine's is one of the most popular. So the null hypothesis in this case would be that the population variance for fallers is the same as the population variance for non-fallers. The alternative hypothesis, as you would expect, is that the variances aren't equal. And both of these will be always tested at the 0.05 level. All right, so now in reporting the equal variance of Levine's test, we typically use a t-distribution, and previously we've seen t, and we'll see it in the write-up here. T, and then degrees of freedom is one number. Well, it turns out for Levine's test, they use something called an F distribution, and there are actually 2 degrees of freedom reported: the first degree of freedom, comma, the second degree of freedom. Again, I'm going to demonstrate this to you. Then you'll have your test statistic, and then you'll report your p-value either as it is or less than 0.05, less than 0.01, less than 0.001. So these are the way that we test the assumptions. So let me get rid of this and give you an idea what the game plan is. The game plan is, plagiarism bad, right? Plagiarism will get you kicked out of school. I want you to plagiarize this document. The only thing I want you to do is when you write up an independent samples t-test, I want you to come in and change this to give the appropriate sample size. You might need to change patients because your cases may not be patients. They may be subjects or hospital staff or whatever it may be, the context of the problem. I want you to report the mean, but obviously put the mean there, or the variable there of the dependent variable, and just follow the format. So I'm going to go through and show you how we make all these calculations. So I already have the data set entered into R. So the first thing I would need is I would just want to look at closed SP as a variable and fall status as a variable. So I would just want to calculate the mean for closed SP. You can see it's 0.86, which I have reported, and I'd want the standard deviation for closed SP, which is 1.07. Numerous outliers. So if I run a box plot for closed SP, what you can see is we have a lot of outliers. You can also see that I copy and pasted that right there. And histogram, I copy and pasted it and placed it right there. Next thing I want to do is I want to dive into the categorical variable here. So I would go ahead and just create a table. I would just call it table. And then I would create a table of fall status. So if I do the table, I can see that 143 did not fall, which I reported right here, and 101 did fall. So I can use prop table of my table to get my proportions. So 58.6% is what I reported right here. Okay, and 41.4% I reported right there. Next thing I do is I come in and put the information in a table, table 1, and I can get some of that information using summary of close SP, where I get the median, Q1, Q3, and I can get the range. The range is from 0.14 to the max of 14.94. And then the fall status is just there. Next thing I do is I transition into the independent samples t-test. So in the last video, I created the research question. So is the mean difference in closed SP significant across fall status? So it turns out that I can run my t-test. And remember, I need variance equal to be false. It's paired, isn't it? Equal false. So you can see that I used the T, degrees of freedom are 208.77, which we have right there. Test statistic 0.24, which I've reported. And the p-value is 0.8, so indicating that the mean closed SP for patients who reported falling at least once. This is where I come in and report the mean, which is given right here. And our report was not significantly different for patients who reported no falls, and I report the mean of 0.87. Now you might be saying, well, how did you report the standard deviation? It's not there. Well, it's easy to do. You use the t-apply command, and you put your dependent variable first, followed by your independent variable, and then just put the command that you want, the statistical, in this case, the descriptive statistics that you want to calculate. So I can see that for none, it's 1.31, which I reported. and you can see it's 0.58 for the other, which I have reported. I say the descriptive statistics for closed SP by false status is presented in box or in table number 12, which it is, or 12, shoot. Table number 2. So table number 2, let's see what I reported. I reported the dependent variable. We could have multiple ones of these. There could be multiple lines, and in most studies there would be. The next thing I have is my independent variable broken down into the first level, not falling. I report how many subjects didn't fall, and then I report the mean and the standard deviation right here. For the fallers, report the sample size, mean and standard deviation are right here. The t-value, 0.24 from the test statistic, and the p-value. Again, this table is really nice because it allows you to, once we get into more sophisticated designs, we may have more than closed SP. I mean, just think about the previous video, the data set that I started with, that I worked with on an occupational therapy study. I mean, there were, oh gosh, probably 20 variables. So I may have, 7 or 8, 10 lines here with different t-tests that I constructed. All right. The only remaining thing is to check the assumptions, and the assumptions failed here. Now, let me back up. I don't think I talked about this. The 244, to find that in R, you use the length command. Length gives you the sample size, so all I need to do is just choose one of the variables. I just chose close SP, it'd be 244. And again, if I just so there's no, if I decided to choose false status, it's 244 as well. So I just choose one of the variables. But moving into the Shapiro-Wilks, the command is very easy. It's just Shapiro.test. And obviously, if we're wanting to know if this sample data came from a distribution that's normally distributed, it could only be the quantitative variable. It wouldn't make any sense to run a Shapiro test, a test of normality on a categorical variable like false status. So I would run that for close SP. You can see that the test statistic is a W equal 0.40, which I have reported. And you can see that our p-value is very small. It's reported at the lowest level of statistical significance, 0.001. So we have a threat to normality. Now, what should we do? We have a large sample. Remember in a previous video I said as long as our sample size is 30 or larger in each group, which it is, it's 143 and 101, then we can proceed without without meeting the normality assumption. In a smaller setting, you may need to switch to a non-parametric test. More about that later. So the next thing we test is we do the Levine's test for equal variance assumption. This takes a little work because for the first time we have to install a new package to make this work. So I need to install the package car. And guys, it must be entered just like that. Car must be in quotation, install.package, not packages. Oops. All right, it was packages. Oops. So what I'll need to do is choose a CRAN. I always just go down to USA. And why not choose Ohio? All these are stable, so it doesn't matter. Sometimes it takes a little bit. So once it gets the command, it's been installed. Next thing I need to do is access the library. Now notice I just typed library, and notice the car is not in quotation now. All right, now once I have the package installed, and once I have accessed the package by the command library car, then I can run the command. The command is Levine, all lowercase, but the test has an uppercase T. Run the dependent variable with the tilde over the independent variable, and you'll get your Levine test. All right, now notice we got a warning message down here. All right, I failed. I should fail this because in a previous video I told you that before we start any analysis with a categorical variable, we need to force it as a factor. And I didn't do what I said I was supposed to do. So let me show you how that would happen. I would just type false status. I would force false status as a factor. And then I would come in and run the command, and I don't get the warning message that my categorical variable was forced to be a categorical variable because I've taken care of that. Now that's not that important for Levine because obviously when we did that, it didn't, it worked, but it just coerced it. Okay, one more thing. We need to set the center equal to the mean and not the median. You might say, oh, man, 0.7128 isn't 0.58. The reason is because we need to set the center that our variances are calculated around to be the mean and not the median. So when I do that, I get the correct values. Now, notice that the degrees of freedom, F, this just says that this probability was based on the F distribution. That's way beyond the scope of this class. Our degrees of freedom are right here, 1, 242. Our test statistic is under the F value, 0.31, and our p-value is 0.58. Now, I did a box plot of false closed SP over false status. If you want to do that, I think it's really a good idea to get a visual. Just run close SP over false status. And you'll get what I call a side-by-side box plot. So you get our dependent variable, close SP, and you get the graphs over the fallers and non-fallers. So for one of your discussion forum posts for this lesson, you're going to be given a quantitative dependent variable, and you're going to be given a categorical with 2 levels, independent variable, and you're going to be asked to write up the results using this format. Again, it's legal to plagiarize here, but you just have to come up with the numbers using R or, excuse me, StatCrunch. Again, I prefer R because you can take R with you. If you ever need to analyze a data set, R is free. You can download it anywhere. StatCrunch, once the term is over and your subscription to this site through Pearson expires, then you won't have access to StatCrunch. But StatCrunch looks and works a lot like SPSS, which is super cool. Some of you may have extra money laying around where you can afford to buy the SPSS license. But again, R is free. All right, enough of me trying to sell you on R. All right, gang, I think I've reported. Let me just double check. Yeah, pretty thorough presentation of a independent samples t-test. All right, that's it. Take care.